Now we're going to look at a design example. And so as I alluded to at the end of the previous video, this is where our Routh-Hurwitz criterion and our Routh table are going to be particularly useful because we're going to be able to determine a range of coefficient values that are going to give us a stable system. So in this example, what we want to do is find the range of some gain k which causes the system to be stable. And we're told to assume that our k is greater than 0. And so notice our k is up here in the numerator of this forward gain in our feedback loop. So again, just like we've seen in the previous examples, we have this unity feedback path. So we can sort of use that sort of simplified numerator over numerator plus denominator to figure out our equivalent transfer function. And of course, that's the first thing that we're going to want to do. As always, when we're making a Routh table, is first we want to find our GEQ, or our equivalent transfer function. And so you can go through and verify that the equivalent transfer function should be k divided by s cubed plus 18s squared plus 77s plus k. So once we have this information, we're ready to make our Routh table. So again, I'm going to use blue to indicate values that are coming directly from our GEQ. So we see we have a third order system. So actually, let me go ahead and write a couple notes here. So we know we have a third order system, which means we're going to have 3 poles. And so we'll keep that in mind as we determine how many poles we have. Well, never mind, because we have a variable value here, but we know we're going to have 3 poles in general. So let's go back to our blue here, and we can say, let's start with our highest order, which is s cubed. We have then s squared, s to the first, and s to the 0. And so we populate our first row by looking at our s cubed coefficient. We skip 1 to go to our s coefficient. If we skip 1, we're then out of coefficients, so we just have 1 and 77 in our first row. As we saw in our previous example with the third order system, we did not need to include a 0 here. Again, if you're unsure, it doesn't hurt to include the 0, but once you get more comfortable, you realize you don't need to include that. For the second row, we're going to come back and add the coefficients that we skipped over. So we have 18 is our s squared coefficient, and then k is our s to the 0 coefficient. So those are going to become entries in our second row here and here. Okay, so now we're ready to figure out the rest of our Routh table, and again, we can add our little bars here if that's useful. So what we're going to see, we can write out, for instance, let's just say that this is B1, this is going to be our B1 entry here, and that's going to be equal to, we're going to have the negative determinant of 1 over 18, so that's these 2 items right here above it, and then the other column is going to be this 77 over 77 and k, and we divide that by our 18. Of course, we have some variable in there, so we're not going to have an exact number, but rather what we're going to have is an expression. So for this entry, we're going to have 1386, which is 18 times 77, minus k divided by 18. And then because we have 2 implied zeros here, this entry is going to be 0. And then what we're going to see is that this first entry here, if we call this C1, we could go through and let's say, to make things easier to visualize, let's say we call this variable x. So we could say C1 is going to be equal to negative 18x, and here we have our k and 0, and we divide that by x. And so what we're going to end up with is, of course, this is going to be 0. So we're going to have 0, so negative 0 minus x times k divided by x. So our 2 negatives cancel out, our 2 x's cancel out, and so we're just going to get a k. And so that's a pattern you'll start to recognize. So basically this term is going to sort of skip over a row and move back 1 column. Again, not necessary that you do that, but just sort of an easy way to confirm you're working through the right thing. And so this entry is going to be 0 because we have implied zeros here as well. Okay, so now we have this Routh table. So let me get rid of that x there. So now we have this Routh table, but we don't have numerical values. So remember though, what we're looking at as we're interpreting this Routh table is we're looking at the number of sign changes. And so the number of sign changes is equal to the number of poles in the right half plane. And so of course, if we want our system to be stable, so stable means no poles in the right half plane. So no poles in our RHP, which means no sign change in our first column. And so that's the first column of our Routh table, obviously. So we're saying we don't want any sign changes here. So now because our 1 and 18 are positive, that means that this 1386 minus k over 18 also needs to be positive. So we can say 1386 minus k over 18 needs to be greater than 0. And so what we can see, of course, the 18 goes away, and we're left with our k has to be less than 1386. So k less than 1386 is going to result in no sign change, which means we're going to have no poles in our right half plane. So sort of what I have written before. So no right half plane poles, which means we're going to have a stable system. Now, of course, we need to consider this k value here, but of course we were told in the problem statement that our k is greater than 0. So because our k is greater than 0, we don't need to be worried about this one because that's going to be positive regardless. So we know if we have positive term here, we'll have no sign change going from 18 to that term and no sign change going from that term to k. So again, this is sort of the real power of using these Routh tables is when we're designing, we can figure out the range of allowed gain or some adjustable variable value.